This bug is about laziness. We have some code that implements some in-place sorting algorithms like bubble sort and selection sort. What we've done is gone to the textbook to understand how bubble sort and selection sort work. We've implemented them, and we've implemented them in a very interesting way. We've implemented them in terms of just the swaps that they do on the underlying data. We've written a test to make sure that our code is correct, but when we run the test, the data isn't sorted. Here, you can see that we first define the swaps for the bubble sort and the selection sort, and then we actually swap the designated positions. And we have a very simple test that tells us, did the bubble sort and the selection sort match up to xs.sort? If we run this test, we'll see the test fails. Can you spot the bug? Well, if you have a little bit of difficulty spotting the bug here, I'll give you a little bit of a hint. And this hint might be giving the game away. Here, we have some structure that we might want to sort. Just like in the original code, we're going to collect the indices. We're going to try and figure out what those swap indices will be for a selection sort. We're going to print those out, and we're going to go through the swaps. And let's see what happens along the way. Does the hint help? Can you spot the bug? Well, one of the things that you probably thought of when you saw this code is, can you really do that? Can you identify all the swaps up front? And in fact, you probably can. And you could probably do this irrespective of what kind of sort it is. Because ultimately, when you think about the sort is just performing some action on the underlying data. And you could always implement a regular sort, just print out what the swaps are and just figure out what those are. And so the question is, can you identify the sorts ahead of time? Yes. Can you identify the sorts ahead of time by creating a list comprehension that creates all those sorts by looking at the underlying list? Probably not. And the reason is, as you see this code executing each one of those swaps, as it swaps each of these values, it changes the underlying list. And as a consequence of changing the underlying list, well, the swap that it thought it was going to do next might not actually be those two indices anymore because you've changed what's at those two indices. You cannot identify the swaps by pre-computing them in this fashion. However, it turns out that the answer is quite straightforward. And it's actually quite simple. This is probably one of the smallest bug fixes that we might see, because all you have to do is change the square brackets when it defines the swaps here and here to parentheses. All you have to do is take what is originally an eager mechanism, the list comprehension syntax, that computes what the swaps would be, and switch it out for a lazy computational mechanism, a generator expression, that will only execute the code that identifies what the next swap will be as you ask for them in the for loop below. And as a consequence of that, every time a swap occurs and it mutates the original data, well, you haven't pre-computed what the next swap is, you're computing that live. And so when you say, what's the next swap, it's going to look at what the state of the data is and correctly tell you what the next swap is. And in fact, when we rewrite the code like this, by only changing those square brackets to parentheses, we end up with all of our tests passing. This is, in fact, a completely valid way to implement both a bubble sort and a selection sort, although it is a very interesting way and a very non-standard way to do this. I actually really like this implementation, in part because it shows you exactly what the algorithm is. For example, a bubble sort is just multiple rounds starting from the end, where you swap each individual item, bubbling them down if the ordering is wrong. And a selection sort is multiple rounds where you swap each element with the minimum element coming after it. And all you have to do is implement this in terms of generator expressions rather than list comprehensions, and you can actually make the code work. But like in all of our cases, I think the explanation is what really counts. And so let's review a couple of important details. When we have a list comprehension, this represents some operation that we can generally write as a for loop with almost complete equivalence. And so if we did something like this, create y's as x squared for x's and x's. This is more or less equivalent to writing something like this. Now, syntax aside, one of the things that we need to keep in mind when we think about, say, the list comprehension is this code here computed eagerly. When we think about eagerness and laziness, what we're thinking about is when we have a computation, is that computation something that can be broken down into parts? And if we can break that computation down into parts, can we then run only the parts of the computation that we want to run when we need to actually perform that computation? In other words, Python actually gives us the ability to take a computation that consists of multiple parts, like step 1, step 2, and step 3, and instead of expressing it as a computation that has not been broken down into individual parts, that's just one big computation that you have to run to completion because you don't know where you can stop, to instead implement it as something that demarcates each stage of the computation such that in this formulation, you can actually run the parts of the computation as you desire. And you can do any arbitrary action that you want in between. And that's basically what a generator or a generator coroutine is all about. It really is just about taking some computation and breaking it down into parts, and then realizing that once you've broken that computation down into parts, not into steps, well, you can run one step. You don't have to run all the steps. You've delineated where one portion of this computation is. Having said that, all the parentheses structure here is all of this generator expression idea. All it is reusing the list comprehension syntax to express the idea of a computation that can be broken down into parts, but where that computation doesn't have any sort of template. It only exists in one instance. So you have one instance of the decomposable computation. And so when you look at the difference between a line that looks like this and a line that looks like this, well, you can immediately spot the difference if you print out the result. Here we'll call this y's in the first case. And in the second case, we'll call this a GI for generator instance. In the first case, you actually get the results. This is what you might call a concrete structure. So you get the concrete results. You get the actual answer. Here, you don't get the actual answer. You get some intermediary, which you can then ask for parts of the answer. You can say, give me the first part of the answer, the 1. Give me the second part of the answer, the 4. Give me the third part of the answer, the 9. Or you can do something that people often call materializing. You can take this and dump it into a list using this syntax or this other syntax like this. So you might say this is materializing this generator expression or this instance of this generator into a list and making it concrete. Well, here, this syntax means I have some computation, something that computes x squared over and over and over, just like you do in a for loop. But I'm not going to pre-compute all of this. I'm going to compute this on this demand when you choose to materialize it in this fashion, or when you choose to step through it in a for loop formulation, or when you choose to step through it using that next or the corresponding send command. In the case of the code that you write, you should be aware of places where this approach is going to be helpful for you. I often see that people make use of things like generator expressions in cases where it doesn't really make that much of a difference. And so, for example, if you think about it, if you have some data and you have some function that maybe takes this data in, and you return, say, some comprehension built on this data, like that. This might be a fine way for you to write your code, and then you can wait down the line until somebody actually needs to do something with this data, and they can materialize this. Bear in mind that the computation that was defined here is only actually ever executed down here when you're actually looping through this. This may be of benefit to you because, for example, if you loop through this computation in this fashion, you don't have to allocate all the memory that's needed for the entire computation. And so if the data set happened to be very large, say range 100,000, well, you don't have to allocate a structure with 100,000 elements because you're only looking at one element at a time. So that's a general benefit. But if it's the case that this function really only ever gives you some output that somebody needs to have in its concrete or completely materialized whole. For example, it's always the case that somebody takes the output of this thing and they sort it. Well, sorting needs every single element at once. And so the use of this generator expression didn't really gain you anything because you know that no matter what, somebody's going to immediately materialize this thing. So you didn't really gain anything. Or if it's the case that every time somebody calls this, they're going to have to dump this into a list because they need to look at multiple elements at the same time or all of the elements at the same time, whatever the case may be. Well, you didn't really gain anything by just writing a comprehension. And you might have even lost something because, for example, if you needed to debug this code, well, this is going to be a little bit harder to debug because you don't have the concrete structure yet. Additionally, there are some additional bugs that can pop up along the way. I'll give you a common example of a bug that pops up when people use generator expressions when they shouldn't. If I am reading from a file, I can go through each line of this file and do something simple like transform it, maybe strip off some white space. And so here, let's do this. And here you can see the output of this is actually the code itself that just run. So here I'll do something like this. We'll do .upper. So you can really see that result. There you go. So you can see that's what the output of this is. Well, let's say I say, okay, you know what? I actually want all the lines of this code. So I'll write my code like this, lines.append. Here we go. And then I'll print out the lines once at the very end. Okay, fine. Then I say, you know what? I could rewrite this as a list comprehension. And that might be slightly nicer syntax than what I started with because now I can, jam everything onto one line like that. And everything's okay. And then somebody says, well, you know what? It's not even that much work. I'll just turn this into a generator expression. Okay, code still seems to work. Okay, now let me actually make use of this data. Well, when you materialize it, the actual work is no longer being done as of this line. The actual work is being done as of this line. And as of this line here, the file has already been closed. It's a very common mistake when you use generator expressions without really carefully saying, do I need to pre-compute this at this stage of the program? And if you combine that with something like a context manager, some resource that you're working with, well, you can accidentally create a deferred computation that only gets executed after the resource is no longer available. And that's exactly the nature of the bug that you see here. And I've seen this before numerous times in code. In fact, you can think this is the opposite version of the bug that we had. In the original code, the bug that we had was that we were running this too early, too eagerly. We were computing the swaps without saying, oh, wait, hold on a second. The data changed as of the last thing that I did, but I didn't reflect that. In the latter case, we're actually saying, oh, you know what? I'm deferring the computation, but I actually can't defer the computation because I need access to it. I need that resource right then and there. I need to do this eagerly. I need to do this while I'm inside that context. Being able to use generator expressions and generators and all of these lazy programming structures precisely to what you're trying to accomplish in your code is a very critical skill set when you're writing Python code. And it's very much the case that when you write some code, especially using list comprehensions, and you think to yourself, does a generator expression really improve this? You should really think, is it the case that somebody actually wants to look at these elements, element-wise, they don't want to look at them all at the same time? Is it the case that they're not going to just materialize it themselves? Am I actually gaining anything? Because there's a lot of small, subtle bugs that you can introduce. One last thing that I want to share with you is the following. One of the tricks that you can use that leans into the laziness is if you have multiple stages of a data transformation, so let's say you have some data that looks like this, and you want to transform it in a number of different ways. And you want to isolate those changes so you can read this a little bit easier. So here you're going to do something like, x squared, x minus 1, and then maybe the absolute value of x. And this is a little bit synthetic because you can think, why couldn't you just do this all in the same line? But you can imagine there may be some steps of some process, or maybe here I'll do if x is less than 0. You can think that maybe jamming this all into one giant line, maybe that's not very valuable for readability, or maybe that's not exactly what you want, or maybe these steps really should be written out in this fashion. Well, it turns out then when you write the code like this, everything kind of works the way that you expect it to work. And you get, in fact, each element squared and then having 1 subtracted for it. And then, I guess since we squared it, we won't have any negative elements. So here we'll say if x mod 2 equals 0. There we go. And here, the absolute value of all the even elements. And I guess the absolute value doesn't really make any sense because these are already squared. So maybe we'll cube them. And we'll get the absolute value of the cube of all these elements. And we didn't start with any negative elements. So here, we'll add in a couple of negative elements as well. There we go. So we get something like this, and this actually works. And one nice thing about this is we don't need to have a bunch of different variable names like we would if we had, say, a for loop, because here, this structure is assigned to ys. So ys is only replaced once we create the structure as a whole, so we can just reuse this variable name. We can end up with some code that's actually pretty easy, easy to read. You start with x's, you cube every element, you subtract 1 from every element, you take the absolute value, and you filter. If you were to change this to some code that uses generated expressions, the code is still correct. And let me materialize so I can show you that the results are the same. One interesting thing that'll happen, though, is this ys here will bind against this variable, this ys here will bind against this variable, and this ys here will bind against this variable. So what you'll actually end up doing is fusing all of these steps into one step. In the previous version, you actually genuinely had 3 loops. So if you had 1,000,000 elements, you'll loop over the elements one time, 1,000,000 visits, another time 2,000,000 visits, another time 3,000,000 visits. But when you do this, it'll actually fuse this together into one structure. In fact, at this point, ys will actually look like something like this. It'll actually, behind the scenes, more or less, be something equivalent to something like that. And what's not to like? This is great. The problem is, if you didn't really need to do this, you can also run into some trouble because this starts to get kind of tricky to debug. And another bug that tends to come up when you have all of these generator expressions, especially those that build upon other generator expressions, is you're going through this code and you're like, oh, something's wrong here. What's wrong? And so you say, you know what? Let me just print out in my debugging what the value of y's is. OK, and then we'll make this an f string. Oh, it's a generator object? No, I actually want to see what the values are. Let me just look at the first value of this. OK, the first value of this is negative 126. OK, this seems to be working correctly. Or let me take a look at what the intermediate step, what the result of the intermediate step is. Oops. Like that. OK, those are the values here. Well, one of the things about these generator expressions is, as a consequence of being one computation that's been broken down into parts, well, you run each one of those parts of that computation without having to run the entire computation. So you can step through that computation, which has its own benefits. But on the other side, you can only step through that computation one time. Generator expressions are very much the case of when you go out into the field and you observe something, you change it while you're observing it. You cannot observe a generator expression, or at least the results of the computation within it, without changing that expression, without mutating it. They are fundamentally mutable elements, which means if you have lots of generator expressions in your code and you want to debug something, well, it's going to be really tricky to debug because you can't see what the computation will provide without changing the computation. And the moment you change the computation, you'll change what the rest of the code does. Because you can see here, once I, as part of my debugging, just spot checked whether this intermediary result is correct, I actually affected the final result. I emptied out this structure. And so there's no more values left. Or if I just look at one value, you can see in between having my debug turned on and having it turned off, I actually removed a value from the end result. And so debugging these things can be kind of tricky. If you do need to debug these things, then what you'll need to do is you'll need to make a copy of these structures. You'll probably need to operate only on the copied value. When you make a copy using itertools.t, this is a transparent buffering copy. This is an intermediary that sits between the generated expression of the generator and the thing that's going to be executing that. Says whenever you execute an element, unless you have asked for that computation on both ends of the t, I'm going to buffer this. So if I ask ys.copy for the next element, ys is actually going to have a little buffer that's going to include all of the elements that, hadn't yet been asked of ys. It's going to buffer those up. It's going to kind of cache them. Well, you'll have to do this in order to debug this. And this starts to get quite clumsy in practice. And so one key thing to remember is generators, generator expressions, they are very, very cool, but you have to use them very precisely in your code because you can end up creating other bugs in your code. And you can end up creating situations where it might be hard for you to find bugs because it's generally difficult for you to debug your code.